Hi guys, welcome back to the channel. In this video we are going to discuss about the concept T flip-flop. So its truth table and its circuit diagram and including its excitation table and characteristic table. So let's get started. So directly jumping into the T flip-flop. So this is the block diagram of T flip-flop. You can see over there. We have one input only, that is T, and two outputs, that is Q and Q bar. So the name itself says that T means toggle here. So we can also call it as toggle flip-flop. So if you directly consider the truth table as well, so when clock is 0 it will not work, when clock is 1 only it will work. So when clock is 1, see the remaining things. So when t is equal to 0 0, the way we have two cases. When t is equal to 0 0, so the present state if changing from 0 to 1, then output will not be toggled for the next state, because in this case t is equals to 0. So t is equals to 0 means don't toggle, that is the situation. So if t is equals to 1 means it is showing that signal that you can toggle now, the present state you can toggle now, that is it is saying, toggle is saying you can toggle now. So when t is equals to 1 for the next two cases, you can also observe that the q present state is changing to the next state, that is toggle to two cases. So this is the simple truth table that I can see. So already we have discussed so many times, there are two types of things, that is positive edge triggering and negative edge triggering. If you are representing the negative edge triggering, we have to represent a small bubble, means before the triangle as shown there. Negative means positive edge means nothing, we can means that the same thing we have to represent. If negative only means the bubble has to be represented, that is the main thing. So the truth table can be simplified in a small and simplified acute manner. If you observe there, when t is equals to 0, the output will be toggled. So sorry, not toggle, that is if t is equals to 1 only, the output would be toggled, means the present state will be in the next state will be toggled. So that you can see over there. So qn means in the previous state, qn plus 1 in the next state. So if t is equals to 0, not toggled. If t is equals to 1 only, it gives the signal, toggle gives the signal, you can change now like that. So it changes in the t is equals to 1. So this is the JK flip-flop as you're showing there. So if you don't know about JK flip-flop, I am giving the video in the description box, check it out. Because with the help of JK flip-flop, we can able to convert with the means we can able to obtain the T flip-flop with the help of JK flip-flop. So if you consider the truth table of JK flip-flop, you can see the first and last conditions are almost similar to the T flip-flop condition truth table. So when 0 0, it is holding the previous state, that is qn. If 1 1, that is toggling the previous state in the JK flip-flop. So with the help of these two conditions, we can able to merge the two conditions and we can form a T flip-flop with that. So let's see how to do that. So in this format, you can merge both of the JK and give a single input called T. So this is the T flip-flop using the D flip-flop. So this is the conversions. So we will cover all the conversions in a separate video, like J to means J to JK to T, T to JK, SR to T, SR to D, anything. These kind of all conversions will be discussed in the separate videos. Just for understanding purpose, this can be possible. So that is why I am showing here. Now let's obtain the characteristic equation of the T flip-flop. So if you observe this, so I have written in the truth table like qn t, qn plus 1. So we have two minterms in the m2 position and m1 position. So we have to the output expression, that is qn plus 1 is equals to sigma 1 2. So characteristic equation means we have to express output expression, means qn plus 1 in terms of input and qn previous output. So if you see clearly, as we have two variables, that is qn and t, we have two minterms. So place the two minterms in the two variable k map and group them. So the first green group is t bar qn and second group is t qn bar. So that is simple XOR. So XOR operation. So t XOR qn. The output expression qn plus 1 is equals to t XOR qn. So the main use of this output expression or the characteristic equation is, if you don't know the truth table, just putting the values of t and q in that and we can able to confirm whether our assumption is right or not. So if you observe the simple t XOR qn, we already know about XOR gate. So if you take t is equals to 0 and q is equals to 0, so the output qn plus 1, what it will be going to have. So both are same, so output would be same, that is 0. So if you consider the last case also, when t is equals to 1 and q is equals to 1, the qn plus 1 is equals to 0. So the remaining between two cases would be 1. That is simple XOR operation that I can say. So those output expressions, that qn plus 1 output expressions, can be compared with the help of the truth table also. So hence truth table is verified and block diagram and this output expression, characteristic expression also is verified. Now we are going to obtain the T flip-flop excitation table. So what is meant by excitation table? So it is nothing but just we are going to obtain the inputs from the outputs. So why this is needed? So this is very important for the flip-flop conversions. So we will discuss in detail about these conversions in the other videos, but we need to have excitation table, the basic excitation table. So the basic conversion from Qn, the present state, to the next state, that is Qn plus 1. So what will be the input? So that is the thing that we are going to find out. The excitation table can be obtained from the characteristic table or the truth table. We can simply say both are same. So the truth table, you see that Qn and Qn plus 1 where there is 0 0. So if you see, that is first case only. The corresponding input t is 0. So place the t in the truth, means the excitation table. Similarly, if you consider the next case, that is Qn is changing to Qn plus 1 as 0 to 1. So if you consider 0 and 1, the Qn plus 1 in the truth table, that is the corresponding input is t, place t as 1 in that excitation table. Similarly, place the two remaining 2 as well in the excitation table. If you see the last one, that is 1 1. So Qn, the present state 1, is changing to the next state 1 also. So if you consider corresponding in the truth table, that is 0, t is 0. Means there is no change from the output. Means what? The toggle condition is 0, the input is 0, that we can understand simply. If the input is changing, or the output is changing from Qn to Qn plus 1 is changing, then it is toggle is 1. If not changing, toggle t is equals to 0. So if you place that as excitation table, in that table it is 0. So this is overall T flip-flop excitation table. So we are going to use this excitation table in the flip-flop conversions. So practice this once or twice so that you can able to have a remember or grip in this. So now we are going to see the T flip-flop circuit diagram. So for the circuit diagram, just observe this. So this is JK flip-flop. So just combine the both of the inputs, that becomes our T flip-flop. So we already discussed in the previous video about JK flip-flop circuit diagram. So just replace the JK flip-flop block diagram with the circuit diagram, that gives our T flip-flop circuit diagram. This is the JK flip-flop circuit diagram. Just attach J and K, both of them, that gives our T flip-flop. So let's join both of them. After joining, you are going to have the circuit diagram like this. So this is the basic circuit diagram of T flip-flop. So the basic logic inside that box is that circuit diagram. So both are circuit diagram and the symbol is both are same. So in the upcoming videos, we are going to see the conversions from T to SR, SR to JK, JK to T, like that many conversions we are going to see. All the conversions will be performed in the upcoming video. So stay tuned. I hope you understood about the T flip-flop. Thanks for watching up to now.